haptic feedback. So now you see that how inefficient the process is. And in fact, you can now compare this video with the video that I showed you in the beginning, where a person was trying to light a matchstick with the anesthetized hand. So that means if we can incorporate the touch, tactile feedback in this hand, this process will be more efficient. And this is just using one hand. So if we can do that using two hands, then it will be much more efficient. So we hope that our findings will contribute to this type of technological developments in the communities. So with that, I would like to acknowledge some of the people who were involved in my graduate school, and I would like to start with Matt. And the reason that I am bringing Matt here is when I was given admission to the graduate school, that was 6 years ago. So the department granted my admission, but the graduate school held up my admission. But I was so interested to come here, and I would write email to Matt almost every other day. So, and when my admission was granted from the school, from the department, I wrote a final email to Matt, something like, I do not know how to thank you. And in that response, Matt said, get here, work hard. That is all the thanks that is needed. You can check in your email. Okay. So I believe that I fulfilled these two requirements. And this, now it's up to Matt whether thanks so much. Okay.
Good job.
Okay, so then I came to the graduate school and I interacted with a lot of people. And at this point, I should mention a lot of names, but for the interest of time, I'll just mention one name, Onda, and it will be similar to the other people as well in the neuroscience department and also in the Cambridge. So Onda was just the go-to person for any type of academic problem. So I do not know how to thank you. Then you can write an email to me. what I need to do, then I know that. Okay, so I would also like to thank my committee, and I do not need to tell you their contribution in words. You have already seen how my project has been shaped based on their recommendation, based on their feedback. So I'm very grateful to them. I should mention one thing, that Andreas had to leave my committee in the last moment, but I recognize his time and contributions just like other people. Now, I have to tell something about this person. And I intentionally pick this picture. This is a Morgan, because, and that picture reminds me the time when I first met with Jeff. So I'm a little bit emotional now. So I'll keep it very, very short. I'll give just one example to summarize my interactions with Jeff. So recently, we got a review back for a paper from a journal. And the editor gave us 30 days to submit the revised version of the paper. But given that I was busy with my thesis defense, Jeff said that he will ask for the extension of the deadline. Then in the next day, I went to his office and I said, hey Jeff, what is your timeline for the resubmission? Because based on that, I will plan for a vacation. And he responded, plan your vacation first, and then based on that, we will plan for the resubmission. And I do not remember exactly how our conversation went from that point, but in the end, he said, define your life first, and then do your science. That was a great statement for me, because I was not used to thinking that way. I came from a completely beginning. So this is just one example that, and there are a lot of examples like that, that forced me to think differently, both for science and also for life. And going forward, and in fact, I feel that I am a different person if I compare myself with what I was 4 years ago. And going forward, maybe I will do the same science that I have been doing in the last few years, or maybe I will do completely different things, I don't know. But the things that I learned from Jeff about life, about culture, that Jeff said something, gold digger stories, and all other things, that will remain me in my life and will impact my life in the coming days. So thank you, Jeff. And I have 2 more slides, then I'm done. So I'd like to thank my friends and family. Some of them are sitting over there, even if today is a weekday. Specifically, I would like to mention my wife, Tina, and she not only made my family and social life easier, like Jeff, she also contributed in my science. So for example, she edited many of the figures that I have shown you today in this presentation, and also in our papers. And she's not a neuroscientist, but she knows, I believe she knows a lot of things about brain, about neuroscience, because she had to listen this type of presentation for the last 5 years. So I'm really lucky to have her in my life, and I really mean it. And finally, this is the final slide, and I think this is the most important slide in this presentation. And these are the people who defined my life in the lab. So I'm not going to explain all the things that we did, but I will specifically mention Sylvia, Lillian, and Liz. We made a great team in the last couple of years. So the very first thing that I will miss after leaving the lab is my time with them in the lab and outside the lab. And with that, I'd like to thank you for coming and your attention, and I'm happy to take questions.
Can you show me again your 5 classes of responses to the boxes? And I just had kind of a question from a neurophysiologist, which I'll pretend to be for now. Okay, great. Yeah, so let's take that bottom group.
This group?
Yeah, the R, we call them RB.
Why don't you go to the previous slide and then
The previous slide is probably bigger. Where you classified them? Right there, perfect.
Mhm.
So RB. Now, if I'm a physiologist and someone shows me that I'm going to say that's not RB, that's just R, right? Because the response isn't determined at all by L. And so I must be missing something about what's going on. And if I looked at the L, I would say that's not really just L, that's L with inhibition, I would say excitation from left, inhibition from right, therefore you get the both being nothing. In the middle is excitation by right, inhibition by left. You understand what I'm saying? And the bottom is, it's kind of interesting that you seem to have an excess excitation by right, which is a right-handed person, so that's sort of why I was curious about that. So maybe I'm misunderstanding in terms of, I'm looking at it like a physiologist, and a physiologist presents it, that's how.
So let me rephrase the question so that I make sure that I understand it. So you're saying that this class is could be considered as the right class, right? Because this is just inhibited by
Nothing's going on with left. It doesn't know left exists.
So in our analysis, we did not consider the excitation inhibition type of thing.
Right.
It's just only the response magnitude depending on like whether it is large or low. Okay.
Right, but I kinda, let's say Jeff now is gonna do monkeys and try to verify your results here in monkeys. Would you tell him, well, I mean, he's gonna look for synapses, right? Synaptic responses. Is what I just said what you would be telling him to look for? Some cells that only respond to right, some cells that, the RPs would be an indication of that. I'm sort of getting at, I tend to think in terms of synaptic mechanisms and circuits and not in terms of high-level models, which is obviously the level you're thinking at. So it might be nice to make some predictions about what a recording, what recorders should look for, what kind of classes and responses should look for. Because my first response was, that's just an R cell, that's not an RB.
Yeah, so I think I'm having some difficulty understanding all the details of this question. But I would say that these classes were, the way that we have analyzed is just based on the responses, not the directionality. But in the going forward, maybe we will we can discuss in the neurophysiology experiments. And in fact, we're planning to run some neurophysiological studies in the lab to understand this type of.
Yeah, I think it'd be interesting to see how your mechanisms are implemented in neurons, right?
Yes. Yeah. So that is basically the follow-up experiments that Jeff is planning to run.
Yeah.
Can I follow up on
Sure.
that question a little bit? Because I think in your model, it's all in the context of Q integration, for example. And so I'm particularly curious about your LR. Like, how does your model, how is it able to capture that if, as you said, there is no inhibition or something like that as follows, if you're putting some weight on your responses to the left and some weight to your responses to the right, and you have both responses to the left and to the right, but none to the combination.
That's a great question. So, he's asking, like, if we see responses on the left for the left hand and for the right hand, but if we do not see responses for the both hands, then how our Q integration model will predict these responses based on these two responses. So okay, let me go to the model now. So here, so for the bimanual interaction, so the prediction for the both hand stimulation, we use this Q combination technique, but that is independent of the absolute response. It's just based on the channel responses. And also, like when I explain this bimanual integration, I just hide the weights. So this is not weighted at all, and this does not depend on the absolute response of the unimanual hand stimulation. So it's just based on these channel responses, and then in the end, we use some weights to predict that neural responses. So does that answer your question?
Yeah, I think just going back to Paul, like it would be interesting to think about how would the brain implement something like that. You're not taking into account the magnitude of the response to the individual cues, right?
Yeah, so maybe our new postdoc is here. He will do that experiment, and hopefully in the next 2-3 years he will get clearance.
So if I understand correctly, most touch of my right hand is being initially brought to the brain on the left side of my brain. But you don't see unilateral equalization of the frequency modulation. Does this mean that frequency responses are computed at a higher order level? Do you think they are downstream and getting input from both parts of the brain? And may this be explaining why you don't see as linear of that?
Okay, so that's a great question again. So the question was, let me go to the slide. So yeah, once again, I could explain that here. So we see that, so Mike was saying, traditionally what we know that if we stimulate right hand, then that will be represented mostly on the left hemisphere. But here, or vice versa. But here we are seeing kind of distributed into both hands or both hemispheres. So that's an interesting point that we discussed in our lab a lot about these findings. One thing is, it is lateralized in the sense that if we count, let's say, these R-type of boxes, that is more abundant in the left hemisphere. So this is one thing. Second thing is, if we see the contrast of the left-hand stimulation versus right-hand stimulation, we also see that lateralization. But in this type of one upper level analysis, I would say, we see that, and in these activities, we see most of the boxes are in these secondary somatosensory cortex in primary areas. So if we would see any boxer, let's say in the primary somatosensory cortex, probably that would show more lateralization. But in this case, we do not see that.
Yeah, I have two questions. Nice work.
Thanks.
First question is about the vibration stimulus. You consider the different frequencies, but have you ever considered the magnitude of the stimulus for different frequencies? Did you fix the magnitude of the vibration?
Yes.
Right.
Yes, so in a separate experiment earlier than this main experiment, we equalized the perceived intensity across the frequencies. And we did not test for different magnitude of the intensities.
And the second question is about adaptation. Have you ever considered the adaptation of the stimulus?
So in this experiment, we did not consider the adaptation, but we had separate study from that. And within this three, I think the stimulus duration was just 3 seconds. So within that duration, we did not test the adaptation. Yes.
Nice work.
Thanks.
So I have one question. When you see the stimulation, so did you see, like, I don't know how is your fMRI is like, did you see any kind of difference between your gray matter and white matter? Like, where do you see more stimulation? Because functionally, anatomically, they are different. Eh? Someone has more cells, another has more axons, and it's just opposite. So is there any demarcation like you detected in your MRI?
So that's a good question, and we did not look at it. Yeah.
So you showed this remarkable, if I understood correctly, tuning in general to this 222 hertz.
Yes.
So that seems to be overrepresented. Are these subjects the same ones that you exposed to the 200 hertz standard in the previous experiment? Maybe they got a lot of experience with that particular.
No, these are, all of our subjects are different from the other experiments.
So there is no reason to, like, it's just an overrepresentation at that particular frequency.
You said, is that an overrepresentation?
Well, it seemed like there were many voxels that were tuned around 200
Yes.
hertz. Is it, like, what do you think it means? Like, why 200 hertz?
So I think that if I understand the question correctly, I said a little bit about that during the presentation. So our afferent systems is tuned to a frequency approximately 250 hertz, or something between 200 and 250 hertz. So that means that our brain is most likely optimized to process the information that is most available to the brain, let's say from the afferents. So
But why is that tuned to, why is the afferent?
What is that?
Why is the afferent information tuned to that
Because
particular
that is
frequency?
that is where our I'd say nerves respond mostly.
I know, but why? you have
okay,
a speculation. Yeah, it's speculation.
So maybe okay. So I do not know. The first thing is that I do not know the answer, but my speculation would be if we analyze, let's say, the natural things, then we see that mostly the frequency is like something high frequency vibration, mostly 100 to 400 hertz. So probably this could be like our evolution type of thing that we're used to get this type of vibration frequencies that is in this range. So that would be nice. Yes.
Maybe a comment. I want to test what Jeff said. When we started working on machine learning and I had questions on cross validation, I would first tell someone, now let's go ask Jeff, and then we figure out, no, let's go ask Shoaib. So, when you
Throw me under the bus.
well, you know. So in your cross validation, you had these two things, right? So you said they have create a model, they have create a model, and test on the other half. But there was one model for both. So
There was one model for both.
in the figure at least, there was just one box that said model. So you
Go to the
yeah,
slide.
and then if you go sorry.
No, that's fine. Here, right?
Yes.
Yes. I
There's
think
only
you're
one
right.
box that says model. So you train with one half, you create a model, and you use the other half to test that model. And then you do it again with the other half, let's say.
Yes.
But you end up using every single person or piece of data you have in the one model that you create. And
Okay.
then you do cross-validation by leave one out, but the one you leaved out was actually part of that model already. Is that right?
Yeah, so.
No, Jeff is saying no, no, no.
Yeah. So
How does that work?
basically, okay, let me explain this two-fold cross-validation first, okay? So what we did, as we can see here already, train with this first half, this model, and when we train with the second half, then that is basically a separate model, okay? So then we take the, then we have two measurements for goodness of fit, right? And average those two, and that is presented here, and the error bar is just deviation. Does that answer your question? So that is not a single model. I mean, in the end, if we want to report a single model, then probably we need to, and in fact we did that, we need to feed a single model with maybe the whole data.
But still, when you do on the right, you do
And the last in the red bar here,
right.
Yeah.
That bar, wasn't it used in your model?
which bar you're saying?
The red bar,
Yes.
which is your leave one out,
Mhm.
wasn't it? I mean, according to this, you used one half and the other half. You didn't leave any one out when you created the model.
Okay, so in that case, this first hub means the data from 7 subgroups. And this second hub means data from the remaining subgroups. So if we have now 8 subsets, that we can consider that as 8-fold cross-validation technique. So we'll have 8 models that will give us 8 goodness of fit measurements, and that is the average.
Okay, so
Does that answer your question now?
So you did the box in the center was actually 2 models.
Yeah?
Yeah.
So in this across subset cross-validation, it will be 8 models.
Blue bars are different than red bars.
Different.
Like, for the blue bars, you get split half cross validation. For the red bars, you get leave one half cross validation.
Okay. Okay. So it's not that the left brings you to the right.
No,
Okay.
not at all.
Okay.
There's the average bar after S8, that's the average.
Good.
Are you happy now?
Very actually.
Awesome.
I don't know what I'm gonna do when you're gone, but that will happen to me.
I'm in Houston, so we'll have access.
Okay, any other questions from the general? Not that much, thank you again. Now, we'll move on to the closing